Hello everyone, welcome to our differential equation class. In this video we go a little bit deeper in the solutions of second order linear differential equations that are homogeneous and have constant coefficients. In particular, we are going to focus on solutions that describe the movement of spring mass systems, and we are going to introduce a classification of those solutions. And we are going to see that this classification is useful in solving some problems, and we are going to see one example of that type of problems. And then, at the end of the video, we are going to focus again on the solutions that describe springs, the movement of springs, and we are going to rewrite these solutions in terms of two quantities that they are called the amplitude and the phase shift of the movement. This type of way of writing this solution is very common in the field of physics and engineering. So that's the plan for today. Let's start with the classification of the solutions that describe mass spring systems. Let's review the system, the mass spring system. We have an object of mass m, positive mass, hanging from the ceiling with a spring. The spring has spring constant k. Everything is oscillating back and forth in a medium of density d. D can be 0 when there is no friction or positive when there is friction. We have our usual coordinate system that is a vertical coordinate system, positive downwards, 0 at the equilibrium position. For example, this spring is out of the equilibrium position, positive this way, negative that way. The system is described by Newton's equation of motion, which say that mass times acceleration is equal all the forces acting on the system, and the forces here are the force of the spring, so which is opposite to the displacement. That is the force, and then the force due to friction, which is opposite to the velocity. So this is the usual expression for the forces. We move these forces to the other side, and we obtain this expression for the equation of the mass spring system. What we are going to do now is we are going to rewrite this equation in a little bit nicer way by dividing by m first. So if we divide by m, we are going to have here that y double prime plus, and then we are going to have d divided by m times y prime plus k divided by m, y is equal 0. And now we are going to rewrite this equation a little bit. Why we are doing this rewriting? Because we want to find the solutions of this equation, and the solutions are going to involve the roots of the characteristic polynomial, and then we want a nice expression for these roots, and the expression for this root is going to be nice if we write the equation in terms of slightly different coefficients. Actually, the one thing we need to do is to multiply by 2 here, and of course divide by 2. So let's move that a little bit over here. We are going to divide by 2, so you see nothing has changed. We are just rewriting the equation. We multiply by 1, so nothing happens on that term. And then this coefficient here, we are going to give a name. To these two coefficients, we are going to give names. We are going to define new names. For example, we are going to call alpha this coefficient that is d over 2m, and we are going to call omega 0 the coefficient that is actually the square root of what we have over there, k over m square root. And why these names? Because exactly alpha and omega, they are going to show up when we compute the roots of the characteristic polynomial of Newton's equation. Notice that alpha is bigger or equal 0, depending. Alpha is essentially a measure of the friction coefficient per unit mass, more or less, and omega is measuring how strong is the spring, again per unit mass, and this is positive. So with these new names, the equation we had above is just y double prime plus 2 alpha y prime plus omega 0 squared, because we have k over m times y equals 0. So now what we do is, this is just Newton's equation. This equation here is nothing more than that. Well, divided by m, so it's nothing more than this. And now what we are going to do, we are going to find solutions of that equation, and the way we do it is the usual way. We write y of t equal exponential rt. That is going to give us an equation for r, which is going to be r squared from the first term plus 2 alpha r plus omega 0 squared, all that equals 0. And then we need to find the roots of that polynomial, so the solutions of this equation for r, and these are going to be r plus minus is going to be equal, the formula is 1/2, then this coefficient with the opposite sign, this coefficient here, so negative 2 alpha plus minus the square root of that coefficient square, so that coefficient square is going to be 4 alpha squared minus, and then 4 AC, so 4 this coefficient and this coefficient, so minus 4 omega 0 squared. Okay, these are the expression for the roots, but now you see we can simplify these two with these two, and then we need to put a 1/2 here, but this 1/2 here enters into the square root as a 1/4. And then it's going to cancel that, and it's going to cancel that. So that's, after all these simplifications, we get that r plus minus is simply negative alpha plus minus the square root of alpha squared minus omega 0 squared. And you see the expression for the root is pretty nice in terms of alpha and omega, and that's why we introduced this alpha and that omega, because we knew that this is going to happen. So maybe we can move this expression a little bit down here, so there is a little bit more space, and recall that alpha is related to the damping coefficient by this formula, and omega 0 square that we have inside the square root is nothing more than k over m. All right, so let's emphasize that in here. And now with those roots, we can r plus and r minus, we can write the fundamental solutions for the spring, which are given by exponential the root with the plus, and then exponential the root with the minus. Now we have the perfect notation to introduce the classification of the solutions of the mass spring system. So we have our roots written in the way we wanted, in terms of the coefficients alpha and omega. Omega is related to the spring constant, alpha to the friction coefficient. The classification is based on the friction coefficient. First, we are going to study the case that alpha is equal 0, which means no friction, because the is 0. And we are going to see that the expression of the roots in that case implies that the solutions have oscillations, that they are oscillating forever without any decay in the amplitude, so undamped oscillations. Then in the next case is when we do have friction. So we have the friction coefficient is positive, but is not very large in that sense. Alpha has to be smaller than omega, because that has to do with this number inside the square root. That is what is going to be called small friction, and we are going to see that the solution behavior in that case, because of the expression of the roots, is oscillations, but they are damped oscillation. The amplitude decreases and goes to 0. But the solution always oscillates. Then we are going to have a critical case, which is when the friction coefficient given by alpha is actually equal the frequency. So what we have here inside the square root is 0, and we have a double root given by negative alpha. That is going to be called critical friction, and we are going to see that the solutions decay for large values of t, and this is called critical decay. This situation is not very interesting in physical applications, because usually what happens in physical applications are damp oscillations, so this case, or the last case that we are going to see in our classification, and that is when the friction is large friction, and by large we mean that alpha has to be larger than omega 0, because then what we are going to have here is going to be a positive number, and then we are going to have two real roots, and that is going to imply that the solution is going to be a solution that decay without oscillations. So this is the summary of the classification that we are going to introduce right now. So now we are going to see why the assumption on the parameters given by these different cases imply that the solution behave, the corresponding solution behave in that way. For that we need the solution formulas in the different cases, and we are going to start with the case of no friction, alpha equals 0. We said that alpha equals 0 is called no friction because it's equivalent to the friction coefficient to be equal 0. And what that implies? Well, alpha equals 0 means if we go to the expression of the roots, that this coefficient is not there, this is not there, and what we have is the square root of a negative number. Well, this is a pure imaginary number and is given by r plus minus equal plus or minus omega 0i, and we can see that this is a pure imaginary number, so imaginary root. And we know that in this case the fundamental solutions of the differential equation can be written in terms of real valued solutions, which are y1 of t. One possibility is cosine here of omega 0t, and the other solution is y2 given by the sine of omega 0t. So these are fundamental solutions which are real valued in this case, and we can see that these solutions are oscillatory solutions with a frequency omega 0, which means that, for example, one of the solutions, the cosine, behaves in this way. We can see they oscillate with constant amplitude, so the amplitude does not decay and oscillates forever, and because of that the solution is called undamped oscillations, so in this case undamped solutions. So the fact that alpha equals 0 implies that the solutions are going to behave in this way, undamped oscillations. This is the case of no friction. Now let's move on to the next case in the classification, which is small friction. And we said small friction means alpha is positive but small in this sense, smaller than omega. In that case, this implies that, okay, that should be an imply. And you see alpha is given by this formula, omega is given by this formula. So from here we can multiply the equation by 2m and by 2m. So this is going to cancel out, and we get that the damping coefficient is given by this expression, but now we have m here and square root of m on the denominator, and that can be simplified into something like d is smaller than 2 and then the square root of mk. So this is the condition of small friction written in terms of the coefficient d. And here is the same condition written in terms of alpha. In terms of alpha is very useful because, well, recall this is the expression for the roots that are given in terms of alpha. So let's copy that expression down here. Let's say here r plus minus is negative alpha plus minus the square root of alpha square minus omega 0 square. So when we have small friction, what is happening is the condition of small friction means that this number here is negative. And we are going to write that number as negative alpha plus minus the square root of a positive number, which we are going to write it as omega 0 square minus alpha square. Now this number is positive, but with a negative sign on the front. We write it like this because this number is positive because of this condition, but what we have in this inside the square root is the negative of that, and that means that the roots have an imaginary part. So now we can write the roots as minus alpha plus minus. Now we write omega 0 square minus alpha square square root multiplied by I. And if we introduce this number beta, that is the square root of a positive number, omega 0 square minus alpha square, recall this number is positive because we are studying cases where this condition happens. So this number is now positive, this number is also positive, and then beta is positive. And in terms of that notation, the roots r plus minus are given by negative alpha here plus minus beta I, with beta positive. Let's put it again, that condition here. But you see, these are complex roots, and we know what are the fundamental solutions in this case. y1 of t is exponential negative alpha t, and then we have cosine of beta t, and the other fundamental solution in that case is the same exponential negative alpha t with a sine of beta t. So this is how the fundamental solution looks like, which are oscillatory functions with an exponential decay. I know this calculation could be a little bit strange here, hard to understand. So before we continue, let's reproduce that calculation with some specific numbers, so we all agree on what we are doing. Suppose that alpha is 3 and omega 0 is 5, for example. So we want alpha and omega satisfying this condition, and this choice it does because alpha equal 3 is smaller than omega equal 5. So we satisfy that condition. But now let's plug all these numbers and see how this works out. So we have r here, r plus minus is going to be now minus 3 plus minus the square root of alpha squared, which is 9, minus omega squared, which is 25. And as you see here, this is what we have written, and here it is, and we clearly see that this is negative, like we mentioned before. This number here is a negative number. So if we want to compute the square root, it's a pretty good idea to write it as negative 3 plus minus the square root of a positive number, 25, minus 9, with a negative on the front, which is what we did here. Then what we have here is a positive number, and the fact that the square root is negative is written explicitly. So this is positive now. So this is what we meant over here. Write it down like this, because this is what we do. So now this has to be, this r plus minus has to be negative 3 plus minus the square root of the positive number, 25 minus 9, multiplied by an I, which is what we said here. Oops, what we said here. And now we do the calculation. What is beta in this case? Well, beta from above is going to be the square root of 25 minus 9, which we know pretty well that is the square root in this case of 16, which is 4. So you see beta is going to be a positive number. Beta in this case is 4, which we said is going to be positive, and it is. And now the roots are simply plus minus are simply negative 3 plus minus the beta, which is 4 I. So we are not doing anything strange when we rewrite the roots in this way. It's just to write it down in terms of something that is strictly positive, and then we call all that thing a number, and the roots are going to be a complex value with real part and imaginary part. Real part, imaginary part. So in this case, the roots are going to be, of course, y1 of t is going to be exponential negative 3t, and then cosine of 4t. And the other fundamental solution is going to be y2 of t exponential negative 3t sine of 4t. So the beta is nothing mysterious, it's just the imaginary part of the root that in general has kind of a weird expression, but it's just whatever, it's just a number. Okay, and these solutions, as we said, they oscillate, but they decay with an exponential in front. So for example, this solution, here it is an oscillation, but the amplitude of the oscillation decreases, and decreases by this exponential, which I don't know why I changed it into 2 if the example had 3. So let's put 3, because this is what we have, and this is 3, and this is 3. And the solution oscillates forever and decays. This is the case of small friction. That is what we mentioned here. Damped oscillation. The oscillations, they are oscillations and they decay. And now we have the critical case. Next, coming up next. Okay. Critical case. Well, the critical case is when alpha is equal omega, because we just saw this case, and now equal, which means that instead of inequality here, if we put here equality, then here we are going to have an equality. And this is what we say over here. Okay, what are the roots in this case? Well, let's recall the expression for the roots. The expression for the roots, let's write them down here. R plus minus R negative alpha plus minus the square root of alpha square minus omega 0 square. But we just said that alpha is equal to omega, so this number here is actually 0. And then we have a repeat root. R plus is equal R minus is equal R0, which is actually negative alpha. So there are two solutions. One solution, the solution y1 of t, we know is exponential negative alpha t, and the other solution, y2 of t, is t times that exponential. This is what we saw in previous videos. We don't need to say why. That is what we shown. And these solutions decay, both decays because of the exponential, but this has a factor here. So this solution starts at 0, increases a little bit, and then decays. So they look more or less like that. The solution exponential negative alpha t is a solution that decays, this solution here. While this solution starts at 0, increases, and then at some point decreases and go to 0. So these are the case of critical friction that is not that important because it doesn't show up in nature much. And the case that is important is the last case, large friction. Now we have alpha bigger than omega 0, therefore the friction coefficient is bigger than this critical number. And what happens in that case? Well, let's go back to the roots. The roots are r plus minus equal minus alpha plus minus the square root of alpha square minus omega 0 square. All that square root. Okay, this condition now says that whatever we have inside the square root is actually positive. So we don't need to move things around. That's positive, the square root is positive, and then we have the two values, plus or minus. So now but this is a funny number, so we are going to call it gamma. Gamma is going to be this number, alpha, the square root of alpha square minus omega 0 square. It's just a number. And then the roots, and this is actually positive. And the root, so two things, is positive, so let's put it here, gamma is positive. But notice one, okay, let's put it down there. Notice one thing, gamma is, if omega were 0, this would exactly be alpha. But because omega is different from 0, this number here is smaller than alpha square, so the square root is smaller than alpha. So this number gamma is actually smaller than alpha. This is going to be important pretty soon. So what we have is the roots plus minus is negative alpha plus minus gamma. Notice that the roots are real, so real roots. But notice that, well, r minus is of course negative alpha minus gamma, so obviously is negative. But notice that r plus, which is negative alpha plus gamma, because of this relation here that the gamma is smaller than alpha, this is also negative. So both roots are negative. R minus, is smaller than r plus, but they are both negative. That's an important property of this case. And then we have the two fundamental solutions are y plus of t, which is exponential r plus of t, and y minus of t, which is exponential r minus of t. These are the fundamental solutions, but notice that because of these conditions on the roots, these are both decaying exponentials. So both decay. So we have this expression. The exponential with the most negative root decay faster than the exponential with the less negative root, but the solutions decay. This is what happens in the spring when the medium has very high damping constant. So for example, a very thick oil, you put the spring in very thick oil, and very thick means this expression here for the damping constant. Then the spring, when you take it out of equilibrium, the spring is here, is gonna go back to equilibrium without oscillations. This is what we are saying here. The spring goes back to 0 without oscillating. That is the case of very big friction. So here we have now a summary of all the cases and the pictures in just one slide. So we were solving this type of equations, we find the roots of the characteristic equation, and we have different cases. The case of no friction, the solutions oscillate forever, and damped oscillations. Then we have the case of small friction, where the solutions have oscillation, but they have also a real part, and maybe it's a good idea to use the same notation as before. The real part here is negative, So that's why we have this decaying, and then we have the critical. So this is how the solutions behave, both oscillate and decay. And let's put again here I'm gonna put the negative sign in a little bit. So let's put it here, negative. Then we have the solutions when they are real, and recall R0 was actually equal negative alpha. So let's put it here, equal negative alpha. And in that case, both solutions decay in that way. And then finally, when we have both roots negative, so maybe it's a good idea to write it as we wrote before, which is more appropriate. So R minus is smaller than R plus, but they are both negative. So in that case, this is how the solutions behave, and I changed the colors here with respect to the other picture. So let's change it again. This is the solution that we called before the red solution. This is the solution that we called before the blue solution. So this is the red solution, and this one is the blue solution. So now the colors match what we had here. Perfect. And this is a small summary of what the classification with all the important components and the picture of the solutions. Now let's use that classification to help us solve one simple problem. Consider a mass spring system moving according to the solution y of t of this equation, the general equation. Suppose that m is equal 1, and suppose that k, the spring constant, is 49. Okay, so that leaves d not fixed yet. Find the interval of values of the damping constant d so that the spring oscillates and decays. Okay, oscillates and decays. That's the important part. Okay, what is the solution of this problem? Solution. Our equation for this case is y double prime m is equal 1 plus dy prime plus the spring constant, which is 49, and 49 is, well, 7 squared. 7 squared y equals 0. How do we find solutions to that equation? In the usual way, we look for solutions that they are exponentials of RT, and what we get is the characteristic equation, which is for R, which is R squared plus dr plus 7 squared equals 0. And we find the roots, and the roots are R plus minus equal 1/2. Then we have minus d plus minus square root of d squared minus 4 times 7 squared. Okay. Now we multiply by the 2 on both sides, and we put it inside the square root, the second factor, and then this is equal, then, so r plus minus is equal to minus d over 2, which, by the way, this is alpha in our previous calculation, so let's mention here this is what we call alpha because m is 1 in this case. And here we are going to have that alpha squared, which is d over 2 squared, minus 7 squared, which 7 is the omega before. Okay, so now we want that the solution decay and oscillate. So we want solution. We want that the solution decays and oscillates. Okay, well, that is going to happen when the roots have the form that implies the roots must have the form negative alpha plus minus beta I. This is the decay part, this is the oscillate part. Okay, where both are alpha positive in this case and beta positive. Okay, but we are going to have this part in the root only when this number here is negative. So what we really need is that, well, the square root, let's write it down this way, the square root of d over 2 square minus 7 square is pure imaginary. Let's write it down as beta I. And that means, let's put it here, that whatever we have inside the square root, which is d over 2 square minus 7 square, that has to be negative. And that is the condition on the damping coefficient, so we have oscillations and decay, which is what we discussed before. So this is the condition, and we can actually find what is going to be d from here. So suppose we have this condition, then this is what happens is that then, if that happens, our square root can be written as so d over 2 square minus 7 square. When d is small enough, this can be written, of course, as 7 square minus d over 2 square with a negative sign on front. And now we are going to have this number to be positive when d is small enough, and then this is actually the square root of that number, which is positive because d is small enough, times I. And this number is what we called in the previous analysis beta. And what is that number? Well, that number depends on d, but the important thing is that the condition, therefore, the condition d over 2 square minus 7 square, well, because d is positive, means that d over 2 has to be smaller than 7, which means that d has to be smaller than 14. So for any, what the problem is, find the interval of values of d so that the solution oscillates and decays. So the interval of d is, d has to be positive because the solution has to decay, but the solution has to oscillate, so it has to be smaller than 14. So that's the interval. And this is more or less how we use the classification, the understanding of the behavior of the solution in terms of the parameters of the problem to solve this type of situations. This is what we have called in the previous case small friction. We end this video with a little comment on how we can write the solutions that we were discussing before for small friction or for no friction in terms of amplitude and a phase shift. And the main statement is the following. Suppose you have any function y of t given by this expression. This could be the solution of the spring mass system when we have small friction, or when we have no friction at all. Small friction is like this, no friction when we have that not in the solution. But it doesn't matter where this expression comes from. Suppose we have a function like that. Then this function can also be written in this way now, where here we have cosine and sine multiplied by constants, and then the exponential. Here we have the same exponential, doesn't matter, but we have only one cosine, and then instead of C1 and C2 and the sine and the cosine, we have a number on the front, and this number here that we are subtracting from the frequency times t. These numbers are called, so the numbers are here. The A is called the amplitude, and phi is called the phase shift. And well, omega we knew. Omega is the frequency of the oscillation. So amplitude and phase shift. And the assumptions on the amplitude is that the amplitude is non-negative, and the phase shift is any number between negative pi and pi. And omega, of course, we always assume it positive. So the theorem says that any function that can be written in this way can also be written in this way, and here are the way we change from one to the other expression. These coefficients C1 and C2 are given in terms of A and phi in this way, which is equivalent to this expression over here. Notice that C1 and C2 are computed when we have an initial value problem with the initial conditions, and therefore A and phi are also computed with the initial conditions. What is the idea of the proof? The idea of the proof is simply a trigonometric identity. So it's left for the reader, but recall that the cosine of an addition of angles is the cosine of the first angle times the cosine of the second, minus, if we have a plus here, then we have a minus here, the sine of the first times the sine of the second. This is a trigonometric identity, and if you use that identity with alpha to be omega t and beta to be negative phi, which is what we have essentially here, then you get from one expression to the other. So it's easy to see that then you can split this A cosine in this form. This is going to be the coefficient C1, this is going to be the coefficient C2, which are essentially given by these formulas here. So the details are left for the viewer. And now we are going to see how we can use this expression in an initial value problem for a mass spring system, and how we compute the amplitude and the phase shift in terms of the initial conditions. And here is a problem about that. Find the amplitude and the phase shift, and of course the frequency, of a solution of the following initial value problem. Alright, so how do we solve this problem? Well, in the usual way, solution. We start writing the characteristic polynomial. So the characteristic polynomial for this equation is r squared plus 9 equals 0. Then from here we get that r squared is negative 9, which means that r plus minus is going to be plus minus 3i. So if we have that, we see that the fundamental solutions of this equation are, or the general solution is C1 cosine of 3t plus C2 sine of 3t. And from here we get that the frequency omega is actually 3. Alright, but we just said that this is the way we write the solution of the spring when we don't have any friction, we don't have friction, so this expression. But now the theorem says, oh, there is an equivalent expression which is given by this formula, no exponential in our case, amplitude cosine. Okay, so we know that also the solution can be written as amplitude cosine of 3t minus 5. And now we need to use the initial conditions to find the amplitude and the phase shift. But to use the initial condition, one of this initial condition, we can use it right now. This one has the derivative, so let's compute the derivative first. Y prime of t. Y prime of t is the derivative of the cosine, so it's negative 3a sine of 3t minus 5. Okay, now we can use the initial conditions. The first initial condition is that 2 is equal y at 0, and that is just a cosine of negative 5. But maybe now is the time to recall two formulas. One, we are going to use it right now, that the cosine of negative 5 is actually equal the cosine of positive 5, while the sine of negative 5 is actually equal negative the sine of 5. Okay, so we use the first formula here, and we end up with a cosine of 5 is going to be equal to, and from the initial condition on the derivative, we get that 6 is the derivative at 0, which is is negative 3a sine of negative 5. But you see the sine of negative 5 is going to be negative sine of 5, so this negative goes outside, cancel this negative sign. And also we have here a 3 that is going to be cancelled into a 2. And after all that, we end up with a sine of positive 5 equal again 2. So these are the equations for the initial conditions that from here we should compute the amplitude and the phase shift. Notice the one thing, these two equations imply that the sine and the cosine are both positive. So because we are recall the conditions on the amplitude. The amplitude is non-negative. If the amplitude has to be non-negative, and the amplitude times the cosine is 2, and the amplitude times the sine is 2, sine and cosine are positive. So what does is telling us about the angle? Well, here is what is telling us. Let's recall the unit circle and the definition of the sine and the cosine. When you have the unit circle, unit because it has radius 1, and you have any angle here phi, the length of the segment intersection of the circle with the horizontal line is what we call the sine function of the angle, and the horizontal segment here is what we call the cosine. But there are different angles. For example, the angle could be here, and then we have this vertical segment and this horizontal segment, or the angle could be here and we have this vertical segment, this horizontal. So the angle could be anywhere here, and there is a convention that the sine is going to be positive wherever you are on this side. The sine is positive and the sine is negative here. So if the segment is vertical down, it's negative the sine, or here. And here is positive, and for the cosine, the signs are on the vertical line here. Cosines on this side are positive, cosines on that side are negative. For example, then sine and cosine positive would be this case, sine positive, cosine positive, and cosine negative should be something like that, and a sine negative should be something like that. Now we know from our initial conditions that we are looking for cosine. The cosine of our solution has to be positive, and the sine of our solution has to be also positive. So we are looking for a solution in this region. In any other region, these two conditions are not going to be satisfied at the same time. So this is just a heads up for later. Okay. So we have these two equations, and from here we are going to compute amplitude and phase shift. How we compute the amplitude? To compute the amplitude, we need to get rid of the sine and the cosine. One way to do that is to compute the squares on both sides and add up. Why? Okay, let's do that and see what happens. Let's compute the square of the first equation and add up to the square of the second. So we are going to have a square cosine square of phi plus a square sine square of 5, and this has to be equal 2 square plus 2 square. On the left side, which by the way is 4 plus 4, which by the way is 8. Alright, but on the left side we pull common factor a square, and we have cosine square plus sine square of the same angle equal 8. But we know that because of the Pythagoras theorem, this is equal 1. So here is the equation for a. A square has to be 8, which means that a is, because it's the positive root, is square root of 8. Alright, we got a. How do we get the phase shift? Well, we grab this equation and we divide by the other equation. And divided by this equation. So we are going to have 2 divided by 2, and this divided by that. The amplitudes are going to go away, and we are going to end up with sine of phi divided by the cosine of phi. This has to be equal 2 over 2, which by the way is 1. But sine over cosine is the tangent. So the equation is that the tangent of the phase shift, so there is no a anymore, has to be equal 1. And we see that if you put that into the calculator or any computer, it's going to tell you that phi, which I'm going to call phi 1, is pi over 4. Now this could be the solution or not, because this, what we found here, what the calculator does is the solution on a very particular interval, on the interval negative pi over 2, pi over 2. This is where calculators work when they compute the inverse of the tangent function. But in our problem, we work on a different interval, in a larger interval, and in this larger interval than the interval of the calculator, there is a second solution to this equation. So there are two solutions, and we need to figure out which one is our solution. So to understand that, let's go back to the unit circle. In the unit circle, recall given an angle here. We said this this segment is the sine of this angle, this is the cosine, and actually the tangent is from outside the circle all the way up to there. This is the tangent. But this tangent has only one solution on pi over 2, negative pi over 2. This is in this interval, this is where the calculator works, and there is only one solution. But we are working on negative pi. So pi, negative pi. And in that interval, there is another solution, which is this one here. This angle is going to have exactly the same tangent. So there are two solutions on this interval. The calculator gives you only one, and you need to find the other solution, which is this one. And you see from here that the solution is actually phi 2 is going to be whatever you found before minus pi. You see from the picture. Whatever you found minus pi is going to give you the second solution, which is going to be a negative angle in this case, and then phi 2 is actually pi over 4 minus pi, and that implies that phi 2 is negative 3/4 pi. Okay, so we have two possible solutions with the same tangent, tangent 1. And how we decide which one is the solution? Well, we evaluate the sine and the cosine. So the cosine of pi over 4, well, that is whatever it is, but it's positive. And the sine of pi over 4 is positive because they are here and on this side, while the other two are negatives. So the cosine of negative 3/4 pi, that is negative, and the sine of negative 3/4 pi is also negative. Well, but this is wrong. We don't want this solution because recall we said we are looking for solution with positive cosine and positive sine, and that means we are talking about this solution here. So this is the one that we are looking for. So the solution actually is phi 1, which is pi over 4, the first solution we found. But depending on the initial condition, it could be the second solution. Here we were lucky. The solution of the problem is the amplitude we found, square root of 8, cosine of the oscillation frequency, which was 3, if I remember correctly, t minus the phase shift, which is pi over 4. And this is how you write the solutions in terms of amplitude and phase shift. So just to finish this video, one little remark. There are two cases. In this example, we went over one case. Our phi 1 was positive, then the phi 2 we saw from the picture is the original phi 1 minus pi. And this is because of that picture. But what happens if our solution phi 1 is here? Well, then we cannot subtract pi because we go outside our interval, and actually if the solution is here, that means this is the tangent, the other solution is over there. So if phi 1 happens to be negative, which is now this picture, then what you need to do is to the negative solution you add pi. So to this negative solution you add pi and you get the second solution. So depending on the sign of the first solution, you either subtract pi or you add pi to get the second solution, and then the initial conditions are going to decide whether it's the phi 1 or phi 2 is the correct phase shift for your problem. That's all we wanted to say about amplitude and phase shift, and this is a good place to stop. See you guys in the next video.